like in the rod where we divided it by the total length of the rod. In this case, we just take the total mass and divide it by the total area of the disk. Okay, so that's our dm, except we're still missing a little something here in that we have this infinitesimal dm, and this is a large quantity here, right? So what do we have to multiply this by? So dx, I heard? Okay, so, and is that it? dy. So we have a mass per unit area, and we're integrating over the area, so we're integrating over 2 dimensions here, right? Okay, so we have our equation for I, we have our equation for dm, and so is this going to be an easy integral to do here? No? So what makes this integral a little bit difficult?
You're integrating 2 variables.
Okay, yeah, so to start, we're integrating 2 variables, which is something, even those of you in calculus, I don't know if you've done yet. No? Okay, so that's the first level of complication. The other level of complication is, say we're doing the x integral. What's the limit of integration?
R, or 0 to R.
Okay, if you're on the x-axis, it's 0 to r, but what if you're integrating up here? So for the x integral, your limits of integration are going to depend on what the value of y is. Does that make sense? In that, you know, basically this disk, it has a different edge depending on what y is. And so this integral is a little bit cumbersome to do. So the way you have to set it up is you put in the limits of integration of the x integration are a function of y. And so that's kind of painful, and I again, don't worry right now about being able to grasp exactly what's going on, but just think about that this is a tool that's out there. And so what we might want to do to make this a little easier is to change our variables. So change our integration variables. And so if you look at this, you can see there's a lot of rotational symmetry in this. So if instead of using Cartesian coordinates, instead of using x and y, what if we use some kind of circular coordinates? Polar coordinates, yeah. So what are the polar coordinate variables? Don't know how to use it? Well, I mean, at least for me, what it usually is you take x and y, form to r and theta. Is r and theta generally what you guys use for polar coordinates? Okay. Okay, so now all we have to do is we need to figure out, basically, we need to figure out what r and theta are as a function of x and y.
Yeah. Well, what if you found x as a function of y, and then you derive that? Then you'd have like dx is equal to something dy, or something dx is equal to something dy, and then you could substitute that back into your dm, and then you'd have everything in one variable.
Okay, yeah. So I'm sorry. What's your name?
Patrick.
Patrick?
Yeah.
So what Patrick's suggesting is that we basically figure out x as a function of y, substitute that back in so that we're back to a one-dimensional integral here. And the answer is yes, you can do that. And it's basically what you're doing is the same thing I was suggesting originally, where you rewrite the limits of integration to where your limits of integration, so say the limits of integration of x are a function of y. When you do that integral, after you've done that first integral, now you're left with a one-dimensional integral in the remaining variable. And so it's an equivalent thing. And you know, for something like this, it's maybe not that horrendous to do it that way. But you know, in general, once you get comfortable with working with circular coordinates, it's an easier way to do it. So just because this is something you probably haven't seen, we'll keep going with circular coordinates. But Patrick's absolutely right. Of that, you know, there's many ways to collapse this into a one-dimensional integral, and you know, one of those ways is to just write out one variable as a function of the other, and solve and fill in. So okay, so on our little circle here, So our r vector comes out like that to the coordinate r. And then theta, since you always want orthogonal bases, so our theta axis is going to be like that. And so the first thing to notice here, the conventional Cartesian coordinates you use, the center of the axis is always fixed right here, and y always points in the same direction, and x always points in the same direction. With these circular coordinates, the r vector points in various directions radially outward from the center, and the theta coordinate system rotates on the end of that r coordinate system. So it's a little bit abstract in that sense. So
is the theta coordinate tangent to the circle?
it's tangent, or it's orthogonal to the r coordinate, basically. So if you pick any point, so if you're picking this point here that's given by the coordinates r, so r points from the center out to that point, and then theta points in the orthogonal direction.
But if the r extended to the circle, the theta axis should be tangent to the circle.
Yeah, absolutely, and that's basically just, with the circle, any radial vector coming out to it, orthogonal to that is tangent to the surface of the circle. So the intuitive way I have for remembering how to do these coordinate conversions, and maybe Nicole has a different way that will be easier for some of you guys. But so I just think about this of that r, just like x and y. So r is kind of a fixed length, and it has units of meters. And so your infinitesimal your infinitesimal chunk of r is just going to be dr. And so with theta, things get a little bit different, because theta has units of angle. So there's a problem already of that, dx and dy have units of meters. And so the fact that this has units of angle, already something a little bit crazy is going on. The other thing is if you think about theta being normalized to the length of this vector, and that if you move a certain angle, the amount of distance you actually move depends on what the radius out to that is. In that, if you're in the very center of this circle and r is 0, then theta is 0 also. No matter what angle you define, you haven't actually moved anywhere, right? And if you get really far away, if you move, if you move some angle, so let's maybe draw it here. So say this is some fixed angle, theta, right? And say d theta is this little piece here, which this won't draw. Okay, forgive the poor writing. So if you're at this radius, then the actual length in physical units of d theta is different than if you're out at this radius. Does that make sense? So that basically d theta in some kind of linear units in terms of meters is growing as you get further away. And so intuitively, or maybe not even intuitively, mathematically, so the length of this d theta element in terms of meters is going to be r d theta. So does that make sense? And that basically the length of this angular segment, when you convert it to meters, is going to be proportional to r times this infinitesimal angle segment. Yeah, absolutely. So that's another way to think about it. And so this has also solved our problem